In the previous two videos, I solved for you the problem of heat transfer to an argon in a cylinder piston device and basically uh, calculated all different terms of the governing equations. There are two interesting points that remain to be understood. First, uh, what I did was to select my heat transfer boundary on the furnace. I said that its temperature is 1200 K. This basically included all irreversibilities in the process inside this boundary. Now, let's do a different practice. We assume that work is reversible and we don't know of any irreversibilities inside this cylinder. So let's separate the irreversibilities here and the place them outside a boundary and select a different boundary. This is our boundary. Let's select that this is our heat transfer boundary. Heat transfer is done here, and all irreversibilities are inside this heat transfer area. See what we can gain from such assumption. You see, if this is the case, the second law would look like this: S2 minus S1 equal Q12 over TB, the boundary temperature for this heat transfer, which is different from 1200 K. And look, there's no irreversibilities now inside this boundary, and all irreversibilities are assigned to heat transfer and they're outside our boundary. So plus 0. S10 is 0 inside the boundary that we have selected. So the change of entropy for argon is 0.361. It has certainly changed its entropy since it has gained some heat, and heat transfer adds to entropy, would equal 208.2 divided by an equivalent boundary temperature, and calculating it TB would equal 576.73 Kelvin. So this is different from the average between 400 and 800. If we had taken an average, it was 600, but that's not a good equivalent boundary temperature. The better equivalent boundary temperature is here. If that happens, the first law remains unchanged, and the it's just the availability equation which would change, and it turns into the 40.39, which is A2 minus A1. You see, I have only changed my boundary, and therefore I have to change my equation, would equal 1 minus 300 divided by, now the boundary temperature is 576.73 times Q, which is 208.2, minus W, which is 83. Work doesn't change, 83.335, and plus 23.81. And that gives us that 40.39 would equal 40.374, which is a good enough result. Now, the final question of this problem is that what would the maximum possible work in this process be? You see, if it was a cycle, we could calculate maximum possible work from the Carnot cycle and write the Carnot efficiency and calculate what happens for the process. Since it's a process, then the maximum possible work happens when this term is zero and this term would get all the work that was basically part of it was lost due to irreversibilities. So to calculate the maximum possible work, we have to write it, we do write it this way. We write this equation, A2 minus A1 per unit mass would equal 1 minus T0 over TB times Q12 minus maximum possible work, which is W, let's call it W reversible, minus P0 times V2 minus V1. And the final term would be 0. Now, calculating this in our equation has a little trick to be careful about, and that is that our work is done, our work is a cylinder piston work, is a moving boundary work, and in itself it has P times V2 minus V1. So to calculate this work is P times V2 minus V1. And when that maximum possible work happens, both this term and this term change. And what you have to do here is to calculate V2 minus V1 first, and then calculate this term to gain the maximum possible uh, work. So the rest of the terms won't change. So 40.39 would equal this term, which is 156.15, minus 350 times V2 minus V1 and plus 100 times V2 minus V1. And the outcome for V2 minus V1 would be 0.46304 cubic meters per kilogram, which was previously, if you remember, it was 0.2381 previously. Zero point 2381. Now, the maximum possible work is, of course, more, and therefore the displacement is, of course, more. And therefore, the reversible work and the maximum possible work would be 350 times 0.46304, and that would equal 162.1 kilojoule per kilogram instead of 83 kilojoule per kilogram. Now our maximum work is 162.1 kilojoule per kilogram. Now this very ideal process has changed everything. Now we know that in this ideal process, where maximum possible work is gained, Sgen equals 0, or Sgen plus n per mass equals 0. Q12 hasn't changed, equals 208.2 kilojoule per kilogram, and W12 is now a new value, has a new value, 162.1 kilojoule per kilogram. It should certainly change what we have in this equation. You see, in these equations, previously what we did, we knew the left-hand side and calculated Q, W, and SJ. Now we have values for SJ, W, and Q, and we shall move to the left-hand side and calculate that for this very ideal case where maximum work is produced for this heat transfer, what other properties would look like. For example, we have already calculated that V2 minus V1 equals 0.46304 cubic meters per kilogram. Previously, for V2 minus V1, we had the value of 0.2381. The other property change that we could calculate is U2 minus U1 equals Q12 minus W12, which where the values have changed, and therefore this equals Q12, which is 208.2 minus 162.1, and that equals 46.1 kilojoule per kilogram. Previously, our U2 minus U1 was 124.88. Now that hasn't happened, and therefore the final temperature won't be the same. As for the final temperature, we may repeat our equation for the change of internal energy as a function of temperature and rewrite it as T2 equals T1 plus 1 over CV 0 times U2 minus U1, and that T2 would equal 400 plus 1 over 0.3122 times 46.1, and T2 would be 547.7 Kelvin, which is, of course, different to that 800 Kelvin we had calculated previously. Finally, we may calculate S2 minus S1, which is the change of entropy, and that is Cp0 ln T2 over T1, and that equals 0.5203 ln 547.7 divided by 400, and S2 minus S1 would equal 0.1635 kilojoules per kilogram Kelvin. And you see that's how we managed to calculate properties when we had the knowledge of the process parameters. We knew the entropy generation was 0, we knew the heat transfer, and we knew the work. And we worked back to calculate our final properties. Well, thanks for watching, and cheers.